This is a video to prep you for tomorrow's torque lab. In the lab, you're going to need a meter stick, a pivot stand. Your pivot stand could be made out of wood or out of metal, but simply something to support the balance. You're going to need some known masses. They'll be provided. And you'll have unknown masses, either PVC pipe or wooden blocks, and either a paper clip or a weight hanger, fancy weight hanger, and a knife edge support. Okay, I'm going to pull the knife edge support up so that you can see it. Okay, it has a thumb screw at the bottom and two knife edge clamps. Okay, you're going to slide that onto your meter stick or half meter stick, and you're going to use that to put into the pivot stand to get this thing to balance. If you put it in with the thumb screw pointing to the top, it's easier for you to lock it down, but it will make it more unstable to balance. You'll find it far easier to place the thumb screw down. Okay? In the lab, the first thing you're going to need to do is find where the center of mass is for the meter stick. So if we assume that the meter stick is uniform, we would start off just guessing that it was in the middle, so I'll put the pivot at 50, okay? And it's not bad, it's close to balance, but it's not quite. So you would want to just slide it a little bit. And the adjustments here are not large, and it requires a little bit of patience. Okay, still not quite there. All right, I think we've got it, okay? So once you find your center of mass, then it should be perfectly balanced with no additional weights on it. So at that point, you would want to take the thumb screw and lock it into place, and also make note of where that center of mass is, because you're going to need that in a later point in the lab. Then the first thing is to find the mass of an unknown. Be sure to record your unknown, the exact block number, whether it's a B or a C block for Mr. Cox or an E block for me. Then you can either use one of the designed weight hangers, okay, or, and I don't have enough of these, I think Mr. Cox probably has enough of them, but in my class, you can use something highly sophisticated like a straightened out paper clip. Okay, and again, I'll call that up. Right? It's just a paper clip that you could hang the weight on and then put this over the meter stick. Okay, you're going to need to work off the edge of a table so there's room enough for the weight to hang. You can place the unknown mass anywhere. Okay. You might want to pick a convenient number away from the pivot, okay? And then I'll use a weight hanger on one side and a paper clip on the other, okay? Then you're going to want to hang a known mass on one side, and again, you're attempting to get the sum of torques to be 0, which means no tendency for it to rotate. Okay, and again, this just requires a little bit of patience. really small movements, okay, and we can get it to where it balances, okay. All right, once you have that, if you record the distance between the pivot and the known mass, and between the pivot and the unknown mass, you can write a sum of torque equation to be able to solve for the unknown. Don't forget to include the mass of the hanger, especially if you're using a hanger on one side and a paper clip on the other, because those would contribute to your torques. Okay? So that allows you to solve for one of the unknowns. The next part of the lab asks you to find the mass of the meter stick. Well, when the meter stick is perfectly balanced, I have no way of knowing how much its mass is. You can't take it and put it on a balance. Okay? But if we move the pivot all the way, not all the way, but drastically out to one side, then it's very obvious that it's not going to balance because all of its weight is acting at its center of mass, which we recorded in part 1. Okay? And now I need a weight hanging from the other side that would allow me to create an equal amount of torque they've got that pretty good. Okay? So again, if I have a known distance from the pivot to a known mass, I can get the torque in the counterclockwise direction. And if I take all the weight of the meter stick and treat it as acting at its center of mass, which I determined in step 1, then I could figure out what the mass of the meter stick is. Okay? That's a second part of the lab. Be sure to record that. And then the last part of the lab is to use what's known as a class 2 lever, where all of your forces are on one side. Okay? And in order to do that, you're going to need a spring scale. And my spring scales go from either a maximum of 5 newtons, 10 newtons, or 20 newtons. They're not very sophisticated, okay? They just look like this. Important that it reads 0 when there's no weight on it, and that can be adjusted by sliding the scale up or down. Okay, so you want to make sure it reads 0 when there's no weight on it. Okay? Then you're going to place an unknown mass in one location. Place your unknown mass somewhere, and then using a spring scale, you can hold it in equilibrium, okay? And given the reading here, I would either move my unknown farther out, okay, or I'd get one of the smaller spring scales, because right now I'm using one that goes up to 20, but I'm only registering a little less than 2 newtons, okay? But you have the weight of the meter stick going down at a known distance, you have the weight of an unknown mass acting down at a known distance, you have a force acting up at a known distance and a known value of force. And again, all of that's producing equilibrium, so you can use all of your known values of distance and weights to be able to compute your one value of unknown weight. You need to use a different unknown for this part of the lab than you used on the first part of the lab. Okay, so I hope that video helps you get through the lab tomorrow in an efficient way. Have fun with it, be patient with it, and produce a good and accurate lab report. We'll talk about the due dates when I get back. Thank you.